Tá, obrigada. Okay, can we go on? I will finish with 2 or 3 slides that are left from the first class. So, about the meridional overturning circulation, the name for those who don't know about this is the MOC, meridional overturning circulation, is the name. You can find it as thermal line circulation, deep circulation, is this convection cell that starts somewhere in the ocean where the water, the surface water, gets denser and starts moving in the deep ocean. Some years ago, 1751, Captain Ellis made some observations of the deep ocean, and at 1,630 meters depth, they found 11.7 degrees centigrades. And at the surface, they had almost 30 degrees centigrades. So they said, the experiment, which seemed at first but mere food for curiosity, became in the interim very useful to us. Let's see why. By its means, we supplied our cold bath and cooled our wines or water at pleasure, which is vastly agreeable to us in this burning climate. But even though they found it nice, the good thing was that Count Rumford realized that no one could find so cold waters there if something like this was happening or wasn't happening. This is a very simple model in which you can learn about divergences and upwelling and getting denser. If you are a water parcel and you are getting colder here at the poles, then if you get dense enough to go down, you will sink. And somewhere, maybe sometimes, it's not up to the very bottom of the ocean that these parcels go. It depends on where they are acquiring their temperature and salinity characteristics. But somehow this is the way in which you can think simply. If water in the ocean gets warmer in the tropics or in the equator, that water will stay there. That condition is a good condition for stratification. Where you have intense stratification, it's impossible for a parcel to sink, because the condition is that it's light and it gets there and it stays there, okay? To be able to sink, that parcel needs to be denser. So that happens where, at least, it gets colder. And then the salinity. But at this time, this Rumford model, sorry for the Spanish, you will find that there are some new slides if you compare the classes that I put in the Dropbox. But then I will give the girls the new classes. Here it says effects of warming and cooling, surface warming and surface cooling. So what really happens in the ocean is that if we are at the surface, in the equator, we will have warmer water, and as we go to the poles, polewards, South Pole and North Pole, that surface water gets colder and colder. If you go down in the water column, for example, 500 meters, you will see that water is much cold. It becomes, from more than 25, it goes to less, in the equator, to less than 10 degrees centigrade. Don't forget that these values are taking the whole ocean and averaging zonally. That's why we have a value for each latitude. Okay? If you go deeper to 300 meters, for example, 3,000 meters, you will see that water is even colder. And if you go to the southern pole, for example, you will find strange things. The blue one is 3,000 meters. The red one is surface. The red one is colder. Okay? So, if you think linearly, you won't understand that. Okay? If you, of course, water at the poles is getting colder. Cooler is okay? Because it's interacting with the atmosphere, which is, for example, in the winter, colder than the sea. So, those things happen. And also, when you have water with salt, what happens with the solidification point? Is that the way it's said? I don't know if I say it correctly. The point of solidification, what happens? If you have conditions, normal conditions of pressure and temperature, water becomes ice at 0 degrees centigrade. What happens with salty water? What's that point? What temperature you need to reach in order to form sea ice? Minus 1 point something. Minus 1.78. What do you do, or what can you do if you are in a place in which roots get frozen? Roots? It's okay? Roads. So there's a message, is a mixture here in my head. Roads can get frozen. So, what can you do in order to have roads without ice? You can throw salt, because if you throw salt, you put down, you make that point of solidification lower, okay? And then you have this, in the poles, then you have this super cold waters. It means that you have waters at minus 2 degrees centigrade, and they are liquid, okay? Because of the same thing, because they have salt in it. At 4,000 meters, it's almost the same pattern. Okay, the next one is about heat fluxes through the sea surface, through the surface. This map shows you, and here there is a small plot for those who understand a little bit more about heat fluxes. Those of the politics and social disciplines, just think about this. The blue regions are the regions in which the ocean is being warmed up. And the red ones are the regions in which the ocean is warming the atmosphere. Okay. Obviously, the radiation, the sun rays reach the surface at the equator much more intensively, and that's why you hit the equatorial region of the ocean. But then take a look at this. What is this? What is this? We were talking about the Kuroshio current and the Gulf Stream a few minutes ago, and it seems that they have the higher values, negative values. Negative means the ocean is transferring heat to the atmosphere, and positive values means the ocean is getting heat, is getting warmer. Okay, why does this happen? Because, these currents that flow polewards are taking warm waters from the equator to the poles. That's the meridional heat fluxes that we talked about at the beginning. But it's also a question of winds here, because dry winds, intense winds, make things easier for everything, for evaporation and for releasing heat, because you have this air mass which is moving. So if you are a current, a warm current, and you are a water parcel there at the surface, you can interact with the atmosphere, you can transfer heat easily, and you can transfer water easily. So that's why these regions, these currents, are reddish, more red than the others. And these regions are very important because here, where the North Atlantic deep water forms, for those of political and North Atlantic deep water, NADW, it's a very famous name for us. We know it very well. We have the, how do you say, la huella digital footprint. Fingerprints. Every water mass for us has its name and its fingerprints. This North Atlantic deep water is very well known. It's a star, like the coccolithophorids. Why? Because there, where it is formed, this famous conveyor belt starts, in a way. The high rate at which this water mass is being formed now is getting slower and slower. And that's the worry. We are worried about that because here, in Labrador Sea2, here, in this, around Islandia, how do you say, Islandia, if you change the conditions, as you said, if somehow the warm water from the Gulf Stream cannot get there, do you remember the movie? ¿Cómo se llama el movie? The Day After Tomorrow. In The Day After Tomorrow, a Russian ship gets to the United States coast, East Coast. No way. This ship does not have any man driving it because those wolves, I don't remember what were they. They ate everything on the ship. So the ship arrived from Russia to the United States coast alone, drifting. That's impossible. Because the Gulf Stream has been used forever to navigate from the east coast of the United States to the west coast of Russia. So, that movie is very good to see after this course, because you will understand every single. They criticize it a lot. People criticize that film, but I love it because it has these little things that may be stupid, but the point is that they want to explain there what happens with this meridional overturning circulation if you cut it, if you change the way in which it works today. Everything can change. Okay, it's the most important part in this Earth system in terms of controlling and the climate and coupling with the ocean and with the rest of the system, of the Earth system. This was for the coffee, but it was late. Okay. Let's go to the other one. Okay. Now we are in the part of climate variability, and I am going to show you some observations. You won't see, I think, more than 2012, something like that. And then I will show you, if I have time, the other small thing that has some predictions for 2100. So we are going to see a little bit about temperature again, heat content, changes in sea level, salinity, and the hydrological cycle. It's too much. Meridional overturning, that is where I want to go. Okay, in the frame of global warming, we have the community, the scientific community has proven that there are changes not only in the atmosphere, but also in the ocean. The ocean is also getting warmer. This is for those who are from the social groups. We normally speak about the variable, like temperature, salinity, and we speak a lot about anomalies. So to have an anomaly, to have a time series of an anomaly, what we do is we average everything that we have, and then we get that contribution, the mean contribution, and we keep the anomalies, the changes. Okay, so this is temperature anomaly. It's not that we have 1 degree centigrade in the atmosphere. It's that there is 1 degree more than the mean value. Temperature trends at the surface. Okay, this is all these things you can look for in the internet. You know, I have here all the links for you to. You can make these maps. Sometimes you can make them, and sometimes you can just pick them. This is annual January, December. So it's a mean annual map for the period 1951-2015. The variable is surface temperature in this case. No, I think it's anomaly because look at the values. When you have an anomaly, you normally have positives and negatives. More than the mean, less than the mean. Changes. And this map shows that the northern hemisphere is getting hotter, and then you have this, the mean, the zonal mean. We have already seen some of this. You average the whole latitude along the whole latitude, and then you have this value. So that's easier to see that in the northern hemisphere you have values of anomalies of 2 degrees. And in the southern, there are much less, okay? About heat content, ocean heat content. Remember these Argo floats, Argo profilers? We can go up to 2,000 meters. So now you will see from the surface to 700 meters, and this one is considering, the blue one is considering from the surface up to 2,000 meters. And again, is a mean, an average. But what we can see here is that up to the 90s, the blue curve is below the red one. And after that, after 2000, the blue curve went over. So that means that when you have the whole thing, remember, 0 to 700 or 0 to 2000. So I am getting more volume of water. Nevertheless, I'm getting more volume of water, it's getting warmer. So what this graph tells you is that the ocean is getting warmer, really. It's really a fact. And that implies sea level rise. Sea level rise, he said yesterday, not only because ice is melting, but also because the volume is getting thermally expanded. Enhanced stratification, you already know what it is. Remember stratification. The mixed layer is getting more and more separated from the other layer, from the pycnocline. The gradient, the vertical gradient for the change, the vertical change in temperature is stronger. The stratification is stronger. A storm can break that stratification or can erode that stratification if it is weak. But if it is quite strong, what happens for example, in summer, that the sun is hitting. The flux is from the atmosphere to the ocean. The ocean is getting warmer and warmer in that small layer. So the stratification gets stronger. It's harder to break that. Decreased solubility. Every gas will change the amount, the concentration that it has within the water body, because when you change the temperature, it changes the solubility of the gases. So the warmer, the less solubility of the gases, oxygen, CO2. And then you will have ecosystem alterations. Ocean heat content in 10 elevated to 22 joules. Here, and comparisons of observed and simulated ocean heat contents. The same thing that we saw, but now we have models and we have observations. And these models, all of them, have included aerosols. Tropospheric aerosols come from the volcanoes. So models take into account volcanoes. And, The brown is greenhouse gases plus tropospheric aerosols only. And here the greenhouse gases plus tropospheric aerosols plus what happens in the troposphere that does not have to do with volcanoes. Everything. Here in the bottom you have the names Agung, Chichon, and Pinatubo. Great volcanoes explosions. So this means that even though you have this, what happens when a volcano explodes? It throws all that stuff, those aerosols, to the atmosphere, and then the atmosphere keeps this layer through which sun rays cannot pass. So normally, when you have a great volcano explosion, you will have cold periods in the temperature of cold periods in the atmosphere of the Earth. So what this is showing is that even though you have these volcanoes and they can change things, there is still a trend, a positive trend, in terms of how much the ocean is warming, okay? Because volcanoes are going back, are the opposite feedback, okay? They will put a layer through which sun cannot pass. So, okay, then we have sea level rise from warning. That means recall thermal expansion, not because of melting. A warmer ocean implies a larger volume. That's why, okay, again, this is thermal sea level in millimeters. Yes?
You said that volcanoes act as a negative feedback on the temperature?
On warming.
On warming. But at the same time, volcanoes release CO2. So CO2 acts as a greenhouse.
Yes, but during the time in which a volcano explodes, the Earth gets cooler. For that time, for the period of time in which the ceniza, ashes stay there, they make a layer that the sun rays cannot pass. So that's why the Earth gets cooler. But then you're right. If a volcano is always in activity and it is expelling things all the time to the atmosphere, of course, those aerosols that are nothing to do, or they have to do with the volcanoes too, for example, to their activity, but not to an event of explosion, not such those events that are recordable in every temperature register, even though paleo data, proxy data. Okay, and sea level rise 2 is everything. This is everything. The changes in sea level with all the components. Recent rise started in late 19th century. Trend is non-linear for the social people. Non-linear or linear is, I have been speaking about this and I haven't made the point. I haven't. Linear or non-linear means that in an equation, in a formula, you have a simple line, A help me, by x plus y. That's it. But nonlinear means that you have one of the variables that is varying non-linearly. I mean, a square or a third or a fourth, whatever, potencia. Don't remember the word. Potencia. Mathematically, potencia. In English? Potential. You see, it's so easy. Thank you, Alan. So, the difference in sea level rise has been this step here. 6 centimeters in 100 years in this part of the signal, and 19 centimeters in the last part. That's why it's nonlinear. Because if it was linear, the changes would have been the same proportionally. Since 1950, 10 centimeters, the very last part of the series. This sea level rise, I have already mentioned, has everything. Has the sea level rise because of ice melting, and the one because of changes in the volume, thermal expansion of the... Okay, are there any temperature trends in the deep ocean? Yes, there are. Bermuda is a station that has been measuring deep changes in temperature for a while, and the trend that they show is 0.47 degrees centigrades in 100 years. And that's very good, but because they continue measuring. That's what we need. We need, in order to show that, to argument that the changes are really happening, we need to have long series in our data. Because statistically, if you have 10, 20 points, it's nothing. You need more than 50, at least, more than 30 data points in order to see if there is a trend. Bema Channel is another place where these measurements have been made, but they stopped, I think. And the values that they gave, is 0.2 degrees in 100 years. So the deep ocean is also showing, I have already shown that it is warming, but here you can see that there is a trend. This is 1960 up to 2008. Again, heat content from an ocean, reanalysis. Reanalysis, we call reanalysis when we mix data. We have modeling results, and then the modelers assimilate data from in situ data, observation, satellite data, and that is called a reanalysis. All the data together. Heat content from an ocean reanalysis based on forced ocean model and temperature and salinity observations from various sources. 5 ensembles are shown for each layer. Because we have the upper layer up to 300 meters, the sky blue is 700 meters, and the violet is the total depth. I think it's 2,000, up to 2,000. So everything here is showing you that the trend is positive. Heat content is not temperature, it's energy. Be careful. When we talk about temperature, it's a state variable, it's a variable. But heat content is in joules. That's energy. Okay? global temperature changes, and everything is showing the same trends. Okay, here they use this Argo profile data from 2004 up to 2008, and they use another set of data called World Ocean Atlas, and they average the first 100 meters. 100 meters is equivalent to, say, 100 decibars in terms of the pressure that that water column exerts. What we can see here is this is a difference between two different sets of data. And here there is another set of data. So what we are showing here is that different sets of data show same things. Can you see here the red thing is like a C? And here, same pattern? Okay. This shows that the changes in temperature are not homogeneous over the global ocean. Okay? Some places are getting warmer, some others are getting cooler or colder. This is what we call a surface distribution, a horizontal distribution. We can do that at the surface. We can go up to 2,000 meters and see that map. But then we have these sections like this. It's like you have the ocean and you cut it in the middle. And then you look at the ocean from the surface to the bottom, okay? The other one was surface temperature. Thus, that does not mean that if it is changing at the surface, that it's not an argument for saying that it is also changing in the water column. So this graph is showing you the same as the other graphs when we talk about the whole volume of water from 0 to 2,000, sorry. Here it goes from 0 to 2,000. And again, there is this difference between two different sets of data. One, I think, is one more modern and the other one older, and that's why there is a difference in terms of showing changes. And you can see that there are, well, this color palette is quite strange, but the higher values, 0.7 and 1.1 in degrees of change. Oh, no, this is not change. This is temperature versus pressure. Yes, it's a variable. Okay, so 7 degrees, not 7 degrees change. It's not 7 degrees more than the mean. It's 7 degrees. And here 2 degrees. So, but as it is a difference, it's a difference. The color shading is the difference. What it is in color is the difference. And what it is in contours is the zonally averaged temperature. That's it. So the difference is between the two data sets. Wait, because I'm confused now. This is zonally averaged temperature versus pressure. This is temperature, what I have in the section, versus temperature, what I have in the y-axis. That's in contours, means 3, 4, 5, 6, 7, blah, blah. And then Argo minus, yes, that difference is in colors. So the difference is showing time differences, because you take different data sets. One is updated and the other one is older. And the other one is the average temperature. So the now, what's the temperature now? And you can see here that the colors in blue, which is the more differences, bigger differences, but negative. And the red ones are the bigger differences, but positive ones. So that means that one set is different from the other, but in one case, when you have the positive differences, one of the data sets is warmer. And when it is negative, the difference, it's because that data set is cooler than the other one, okay? It's like, what can we do to see if really if the ocean is getting warmer? Okay, you have a series that you have measured for a while, 2000 up to 2008. This is, I don't remember the period. And then you have one which is older, for the same place. So you make the difference between those two series, and the differences will tell you if in the older period the sea was warmer or cooler than in the up-to-date period, the actual period, the current period. I think that's the point, but I don't know if I got to a point there. Sorry. Okay, temperature changes in the Southern Hemisphere. Okay, there have been, this is how we see the Southern Hemisphere. The cartography, the projection, the geographic projection that we use to see the South Pole or the North Pole is a polar projection. So you get there, down there, and you look at the pole, at the southern pole. And what you can see here is recent temperature changes in, well, again, we are going to density. This is difficult for those who are not oceanographers, but when you are over one of those density surfaces, you fix something. You fix density. So you are drifting over a surface of constant density. And then you can see if there are differences between one surface and another. Here they chose 26.9 and 27.7 because those density surfaces are special for looking at displays, you know. That's, of course, people who work there will know what surface to choose, the perfect one. For example, if I want to show you where the base of the thermocline is, or the base of the mixed layer is, I can choose a temperature contour. In Argentina, in Spanish, we call it isotherm. I can choose an isotherm. And I can say, where is the 18 degrees centigrade isotherm? Is it at the surface? Is it at 20 or 30 meters depth? So I use a surface in which temperature is constant in order to see if there are any changes. If that temperature surface, if that surface of constant temperature moves in the vertical, it means that the mixed layer is getting shallower or is getting deeper. Okay, this is something similar, but choosing densities over surfaces. And what we see is lines that represent geostrophic streamlines of the Antarctic circumpolar current, approximately following. Okay, there's much information here. Around the southern pole, we have the ACC, Antarctic Circumpolar Current, a very special current, one of the most strong currents over the world ocean. It transports millions of cubic meters of water. South of the position, of the mean position of that current, you are in an Antarctic climate. North of that, you are in a subantarctic climate. So it separates environments completely. So what this graph is showing is that things are happening differently, south of those lines and north of those lines. Again, showing that temperature changes are happening, but they are not homogeneous everywhere. They are not the same. Increased South Hemisphere westerlies and expected variability. Okay, remember the westerlies. I don't know if I have them here. Wait, because if not, you're not going to understand anything of this. Maybe it was already open. What were the winds? Okay. These are the winds zonally averaged. So this strong, that I was showing you before, this strong wind stress corresponds to strong westerlies, winds coming from the west going to the east. The Antarctic circumpolar current is under that wind pattern. They are coupled. One influences the other. So now try to do this. Try to put yourself like if you were a parcel, an air parcel now. You are in the air now, not in the water. So you are an air parcel and you are flowing with the westerly winds, okay? Ready? So when we see the slide, you will see a circle with a point in the middle, and that means that the parcel coming from the west is going out from the blackboard. It's not a blackboard anymore. Okay, this is it. So this point here, you can see the circle. The westerns are coming out, going to you now, okay? So you are standing, Antarctica is there to your left, okay? So the westerlies are going out, and if you are in the sea now, you are in the middle of the Antarctic circumpolar current. Everyone's situated, yes? Anyone who is not located in the middle of the Antarctic region? Is it cold there? Okay, south, north. So we will have cold, fresh water at the surface, and then warmer and saltier below that one, cold and fresh, because at the surface, water parcels are receiving fresh water from ice melting. That's why it is fresh. Fresh means less salty. Cold because it's in contact with the atmosphere, and the atmosphere is colder. And then the water below is warmer and saltier. Obviously, it's not warm. It's in Antarctica. It's not warm. It's warmer, relatively speaking. So it gets, here is where it gets denser. But here, we can see an arrow that is going up. It's not going down. How is that happening? These are those isopignals, contours of constant density. Those contours are really surfaces. The contour is where the surface touches the line is where the surface of constant density touches I don't know how to say it. Okay, so isopignals that have certain orientation, changes in slope, show that there are currents there. We call them geostrophic currents. I'm not going to put that concept, I think, now. But the point is that here, in the very south, the water is getting denser and goes down. But here, a little bit to the north, the opposite happens. There is a divergence at the surface. So there is water that is coming up to fill that space, okay? Empty space somehow. Because if you have divergence at the surface, you will have like como un deficit, like a deficit. Okay, all these things, all this graph is showing really that there are increased, if there are increased westerlies, if the westerlies are stronger now because of climate change or climate warming, we are going to expect, we can expect for variability in the circulation. Because the atmosphere and the ocean are coupled. Those modelers here in the room can say that they work with ocean atmosphere coupled models, because some of them respond if you put a field with change, for example, temperature at the surface of the ocean, and you use that as forcing to the atmosphere will respond. But then the atmosphere changes and it forces the ocean. That's a couple system, okay? It goes back and returns. It goes and returns. Okay, I'm tired. This is changes in salinity, global changes in salinity. Again, the same difference. Argo, 5 years, in contrast to World Ocean Atlas. First 100 meters column, water column. And the brownish are positive and the blue ones are negative. So this difference between periods is showing that there are also changes in salinity, okay? Here, there's a friend here in the picture, Virna. She lives in Italy now. She is using that instrument, big thing, to measure conductivity. Because, as I mentioned before, we have this CTD instrument that goes down and up in the water column, and it measures all the time. We have to be careful, because that could work wrong. So this is to be able to calibrate and to be able to control the other instrument. Very important, because this one has a better precision than the other one. So we can, as I mentioned, the range of salinities is so small, the same as in density, it is so small that we want to see very, very little changes, like 0.001. So if I don't have very good precision, I cannot resolve those changes. Okay? Global water reservoirs and fluxes. Okay. Water reservoirs. I mean, this is the water cycle. You can see many different schemes of the water cycle. What we would like to tell you about with this slide is that the oceans, obviously, the ocean has the bigger reservoir of water. The squares or the rectangles are sources or sinks, fuentes or resources or sinks, and the arrows are fluxes. Water goes from one source to another, or from one reservoir to another. And the numbers. So bigger arrows means that the flux is in a bigger amount, and smaller. For example, how much water goes from land to the ocean? Rivers, 1.3 svarups. Svarups is a unit that we use to say million of cubic meters per second. For example, an example that I have like this is Río de la Plata outflows 20,000 cubic meters per second, and during an El Niño event, it goes up to 80,000. It goes 4 times the normal value, the mean value, in these same units, cubic meters per second. So, 16 in the atmosphere, 59,000 in the land, and 1,004,000 in the oceans. In terms of, it's easier. In terms of these numbers are more easy to remember. 96%. The ocean is 96% of the water in the world. And here, 4%. It goes like, who is this? Rivers and agua subterránea. How do you say? Watershed. ¿Cómo? Agua subterránea. Groundwater. Thank you. The numbers are not well estimated. Still not well estimated. This is the same as the other one, a section showing the changes in salinities. And now this is the average. It's easier to see that the bigger changes are occurring near the equator, in the tropical areas. And here also, there is a considerable change. P minus E is precipitation minus evaporation. This is a variable that we use very much because it's very close to what happens to salinity. If you see what happens to the variable P minus E, and you see what happens with salinity, it's like they are coupled. It means that salinity at certain places, as she said, if you are in a particular place like the Antarctic or the Arctic or at very cold seas, you may have different things. But if not, and here it says P is greater than E, and here, for negative values, E is greater than P. So where evaporation evaporation is greater than precipitation in the equatorial band. And then if you go a little bit north and south, you will have the maximum precipitations because, sorry, I'm saying it all the way around. The maximum of evaporation are coincident with the maximum winds, because it's easier to evaporate if you have dry winds, the same as we said over the currents. So in the region of here, in the region of the equator, we will have more precipitation than evaporation. I was saying the opposite. Sorry, but I will pass some of them because it's okay. Surface thermal line modification. This is important. It's not an easy concept, but it's important. This variable, surface buoyancy flux, is like you have the yellow ones and the blue ones. The yellow ones are positive, the blue ones are negative. Positive values indicate that the ocean becomes less dense. Positive values. It means that if it becomes less dense, it's comfortable there. Imagine a parcel which is at the surface and it gets less dense. There is no way for her to go down. She will stay up. But if you have these blue areas here, it means that it's easier for a parcel to sink. So those conditions make this region here a good region for forming new North Atlantic deep water water mass. North Atlantic deep water. Here, for example, in the Weddell Sea, Antarctic bottom water is formed. Antarctic bottom water, ABW, and the other one is NAGW, names of water masses. Those water masses, one of them comes from the north and the other one comes from the south. And they get together but not at the same level. One goes up to 1,000, 1,500 meters, and the other one goes very close to the bottom. That's why it is called Antarctic bottom water. So, that's the schematic of this. The movie. Remember the movie. Where was the boy where this old man died? Remember the man that died, the scientific that was there in that laboratory in the north? This guy was paying attention to a boy that was fixed there, and they started seeing that the temperature there was getting cooler and cooler. So this is that place. This is that place. Rho 1 means that this brownish water is less dense. And Rho 2 means that the sky blue water is more dense. So when it gets denser, it goes down and it starts sailing, navigating, not sailing, sorry. It starts its way to the south. Imagine now that this here is the North Atlantic, the North Atlantic. And this blue one is the North Atlantic deep water that is being formed. The brownish here is, don't pay attention to but for the oceanographers you can. This is variation in temperature with the vertical, with it, and this is a quadratic variation. It means that there is a balance here. So the denser water goes down and starts its way, and somewhere it has to appear again at the surface. For North Atlantic deep water, that happens in the Weddell Sea in Antarctica. If you have winds, now this seems to be Antarctica, and these are the westerlies, the ones we saw before, and this could be that water which is upwelling, not right close to where Antarctic bottom water is formed, but north, a little bit north of that. This wind, remember Ekman transport? To the left in the Southern Hemisphere, to the right in the... Okay, this wind, through this balance of Ekman transport, is making water go to the north. And again, this deficit of water should be filled with water that comes from levels that are deeper. All this is to understand really the MOC, the meridional overturning circulation. Now, this is the North Atlantic, this is the South Atlantic, always the Atlantic. Why not the Pacific? Why not the Indian Ocean? Because, first of all, the Indian Ocean is the northern part, the part of the Indian Ocean that belongs to the Northern Hemisphere is much more, at low latitudes. It doesn't reach cold regions, okay? So, but the Pacific and the Atlantic do. They have waters at the very cold regions. So why everything happens in the Atlantic and not in the Pacific? Okay, the Pacific is fresher, it's more, it's deeper, it's very different to the Atlantic. But the Atlantic has, in these extremes, the North Atlantic and the South Atlantic, in the Weddell Sea and in the Ross Sea, there are special conditions in which deep waters or bottom waters can be formed. Any water gets new characteristics of temperature and salinity at the surface because it interchanges with the atmosphere. When it is already at a deeper level, it cannot change much. It can change with a layer which is over and the layer which is below, but it would be little. The strong changes can be for a water mass when it interacts with the atmosphere. Okay, the way for a water mass to lose heat is being in contact with the atmosphere. No other way. So, in the Atlantic, you will see here, you see the little ice, and here too. Here there is a loss of heat, here too, the red ones. I'm not going to read the references. Let's try to understand it without reading the references. Well, there are some of them that I won't talk to you about. But this is simple. Loss of heat here and here at the North Atlantic and at the South Atlantic. These 2 points are the westerlies. This is the Antarctic circumpolar current. This is the thermocline. Question. Pay attention, everyone. How is this called, the blue thing here? The limit is the thermocline. Then I have something of another color. How would you call the blue layer which is over the thermocline? Mixed layer. Very good. Mixed layer. That's the mixed layer, the one we were talking about earlier. The thermocline is the stratification. The index of stratification is how many isotherms get together in the same space. If I have a space like this and only one isotherm passes through, that's weak stratification. If I have many in the same space, many isotherms, meaning that the change is abrupt in the vertical, that's strong stratification. Okay? Here, that stratification is drawn only with this black thermocline line. The lower part is the deep ocean. So you can think of the ocean as a three-layer column. Mixed layer, thermocline or pycnocline, and deep layer. Okay? So here, this yellow thing is North Atlantic deep water, which is being formed there in the Atlantic, North Atlantic. Here, there are some special characteristics like a pool, and a subsurface pool. It gets filled in, and the water passes like. It gets filled here, and at some point, it goes over this, and it's a derrama, how would you say? It flows, helped by the topography. If that topography weren't there, maybe that wouldn't occur there. Thank you. Okay? That's another special thing about the North Atlantic. And then in the South Atlantic, for example, in the Weddell Sea, you have also a very, very steep slope, which is also helping water to go down. Because this one goes up to the bottom. The other one, North Atlantic deep water, here's the name. North Atlantic deep water goes at a different level. But this one, which is Antarctic bottom water, goes down, more to the bottom. And here is the name, Antarctic bottom water. It has another A, but Antarctic bottom water. So this overturning circulation is the famous mock. How do we know that it is slowing down? What does it mean that it is slowing down? It means that the rate at which this North Atlantic deep water is being formed is getting slower, it's getting smaller, the rate. 20,000, I would say any number, 20,000 cubic meters per second. No, now it's not 20,000, now it's 5,000. The numbers are anything. Don't remember these numbers. X and Y, okay? It reduces the rate at which it's being formed. And that can be measured. Okay, warm water and cold water. And this means that if water goes, for example, the North Atlantic deep water goes from north to south, close to the continent, and Antarctic bottom water goes to the north, more in the base, in the deep basin of the Atlantic. Another same thing, another schematic. You may write conveyor belt in the internet, images, and you will find a lot of them. This is Kulbrot, 2007. N, L, W, R, ACC, Antarctic Circumpolar Current. N, L, Labrador Sea, and Nordic Seas. All these points drawn like a little yellow circle are deep water formation places. So here in the Nordic Seas, in the Labrador Seas, in the Ross Sea in the Antarctic, Weddell Sea in the Antarctic. Stop. No other place. So, as they are very special places, if those places change conditions, we are in problem. Okay, the same thing. Vertical stratification, similar to buoyancy, to the variable that I showed before. Strongly stratified is a place where sinking water cannot make it. Okay? If it is strongly stratified, you cannot make a parcel from the surface go to deeper layers. You need weak stratification. You weak homogeneity. You need to have a water column that is almost all cold in temperature, homogeneous. No, there is no mixed layer. Almost none mixed layer. Okay? Do you understand that? You are almost slept. No importa. Doesn't matter. I know it's hard. What I can do is, because I'm leaving at 3 o'clock or something like that, 2 and a half, and I have some assistant that should stay and represent me with the other pupils, with the other students. So I will call them by their names. Alex, can you raise your hands? Alex, hello. Ana Laura. Hello. Deborah? Not here. Lucas. Luciana. Where are they? Luciana. Myla. Hi. Mariana M. Mariana M and Mariana Paul. No Marianas. Marilia. How nice. She's just like, don't be afraid. I'm just joking. Mohamed. No. Mateus. That was with me yesterday, Mateus, I think. No. Thomas. Paula. Thais. Okay, very good. Now, I made a first research and all the participants and found that had graduation in oceanography, so I wrote down the names in order to ask them not to get bored in my class. Okay, I have little time, but let's see. This is again the meridional fluxes. This is the way in which you can measure what is happening with the Atlantic, Atlantic meridional overturning. You can measure transport. Cubic meters per second, this variable in Sverdrups, and you can measure it, for example, across a surface, a section. The black line here is that section, and transport is being measured there, to the south and to the north. Currents, velocities in the ocean are being measured there, and you can then calculate through this section, you can calculate the transport, how much water is passing through that section in terms of time. So, as you can see, there is a tendency to get smaller values. That is the argument to say that the Mach is slowing down. Petawatts in heat fluxes energy. Okay, so that is the Mach drop. Then you can listen to the Mach collapse. That's worst, the Mach collapse. If it is slowed down, well, it's the same thing, but slower. But if it collapses, it no longer be the same. I mean, maybe one of those Christiana systems in which it gets into a different state of the system and never comes back. We don't know. Okay, there are thermal feedbacks. Maybe that's what you were asking for, I think. Thermal feedbacks. The overturning, something is happening differently to one side or the other of the region in which North Atlantic deep water is formed. Negative temperature anomalies at 50 meters at a very moment of slowing of this Mach. And negative and positive means that the changes are that it's getting colder here at the north western part, and it's getting, at least at one of these events, it was getting hotter or warmer, at the southeast side of the place where this Mach starts. The greater the temperature, this is kind of index for overturning. The greater the temperature, the greater the overturning. These points here, that's why thermal feedbacks. If it is warmer, then the overturning is more intense. If it gets cooler, then the overturning gets slower. That's the thermal feedbacks. You can go and see this Ransdorf and England 1997 if you want to see more of this. This one I will show you in another one, Okay, and again, trying to measure the differences in overturning circulation. And let's arrive to the summary. So, the ocean contributes to about 30% of the meridional redistribution of heat on Earth. One way to redistribute is through currents that transport warmer waters like the Gulf Stream. It takes waters that are warmer in the tropical regions and it flows to the north. That warm water reaches a cold region where it it transfers lots of amounts of energy to the atmosphere. 30% of that meridional heat flux is made by the ocean. Buoyancy fluxes, surface wind stress, and vertical mixing sustain a vigorous meridional overturning circulation in the ocean. Buoyancy fluxes, the map that I showed you, if they are not like that in the North Atlantic deep water could not be being formed there. Vertical mixing, it's that means that vertical mixing, if you have water that is denser at the surface and it goes down, that's vertical mixing, because it's mixing, because it's transporting water, cold water to lower levels, to deeper levels. You don't have a mixed layer. You have everything mixed. Particularly in the Atlantic basin. That means it's not that it's not happening in the Pacific, but the intensity of this overturning circulation is stronger in the Atlantic. The MOC also contributes to the meridional heat flux, which is largest in the Atlantic and Indian Oceans. Models and observations show that there are large changes in the intensity of the MOC and the associated heat transport. This is confirmed by models and observations, that there are large changes in the intensity. It's getting slower. The rate at which North Atlantic deep water is being formed is smaller. Recent warming of the upper ocean may be associated with an acceleration of the hydrological cycle. Well, I don't know if we saw that in the slides, but I said something about the hydrological cycle, that it's having a positive feedback. What is salty, it's getting saltier. What is fresh, it's getting fresher. That's an intensification of the water cycle because of global warming. There is strong evidence suggesting that these changes in the freshwater forcing at the surface have led to changes in water mass properties and circulation, whose impact on the MOC is still poorly understood. There is strong evidence suggesting that the changes in the freshwater forcing, buoyancy fluxes, freshwater forcing, it goes together. If you have freshwater forcing, it means ice is melting, so you will have freshwater forcing. That means that you will have a less dense layer, stronger stratification, and you will inhibit. You are not enabling dense water formation. You are cutting it. Okay, because you are strengthening the stratification, and that can have impacts to the North Atlantic deep water formation. As she said, if you have a lot of fresh water, the conditions of salinity at the places where North Atlantic deep water is being formed will change. So the waters in the North Atlantic, they get there already salty, because they are waters from the Gulf Stream. They are already salty. They get there already salty. They get cooler. So they become denser twice, because they are salty and because they are getting cooler. If you change the conditions there, that's why we speak about a collapse of the MOC. Thank you. questions? I'm going to die.
Hi, I'm Rafael from Brazil. Thanks for the lecture. Yeah. I have a few questions, but I try to make shorter. You talk a little bit about upwelling, and we know the upwelling regions are the most important areas for fisheries production. And I am wondering if you have like some ideas about the upwelling process or locally with climate changing or something like that. For example, they are becoming more frequent, less frequent. I don't mean the big upwelling areas. I mean more locally, where it affects local fisheries production, for example.
There are many different kinds of upwelling.
Yeah.
You have equatorial upwelling. You have coastal upwelling. You are speaking about coastal upwelling, for example. Sorry. So, for example, there is a center of an anticyclone in the South Atlantic, which is moving south because of climate change, because of climate warming. So, if you have a semi-permanent, in the atmosphere, you have a semi-permanent anticyclone where, as you know, winds blow in our hemisphere, in the southern hemisphere, it goes anticyclone, counterclockwise. So if you move, you have air moving around the high pressure center. You have air moving here. Let's do this. You have air moving here, okay? And at the top of this, winds blow like this, and at the bottom, winds blow in the opposite way, okay? If you move this northwards or southwards, the local winds, the local patterns of winds change. Because, for example, maybe your coast is here, and you have winds blowing like this. Those are not upwelling favorable winds. But these ones, for example, if you have the coast like this, and winds are in this direction, in the southern hemisphere, because of Coriolis, of Ekman balance, the transport would be to the left. Many places in the Brazilian coast have coastal upwelling, like Cabo Frio, for example. So if you have a wind in this direction, Ekman transport will put water offshore, and there will be upwelling, coastal upwelling. Okay, that's a condition to have upwelling, coastal upwelling, due to winds, local winds. But if your wind pattern changes because of global warming, the anticyclone moves, then you won't have upwelling there. Maybe you have upwelling somewhere else.
Do you know any studies on these issues?
Yes. I have so many things to show, but I don't have time.
No worries. I have one more.
We did. I could send you something. We did. We have these things, but not trying to see differences or different patterns in upwelling, but in sedimentation erosion of coastal of beaches in Argentina, in the south of Buenos Aires. We already found that there is a place where erosion and sedimentation have changed because of different ¿cómo se llama? Littoral, ¿cómo se llama? Corriente costera, due to waves, a longshore current. If you change the pattern, the wind patterns, you change the wave pattern, and then you may change the longshore drift, and can have different results in terms of sedimentation and erosion.
Yeah, that's a bit of my second question about the La Plata plume. We know that there are some events that the plume reached the Rio coast. We have a few years ago, we have some scientists that say that. I wonder if you know anything, something related to this current, something maybe mesoscale movements.
Can you repeat what happened?
Yeah, the La Plata plume going northwards, reaching the Rio coast.
Okay, Rio de Janeiro.
Yeah, the state of Rio coast.
Okay, yes. Yes.
So it's not common, but it happens.
It's common. It happens seasonally. Seasonally, because you may have differences in the scale of the latitude that it reaches, but the Plata plume seasonally, winter and summer, moves to the north and stays close to the discharge, the river discharge, because during winter, alongshore winds are predominantly from the south. So the plume is so light because it has fresh water. So it's a shallow mixed layer dominated by salinity, and it's very easy for the wind going northwards to move that plume. So what we studied is that no matter how much discharge, no matter if it is 20,000 cubic meters per second or 80,000 cubic meters per second during an event of El Nino, but it's the wind what it matters, because the wind can move that plume northwards, and you can have events that get to Rio de Janeiro. Not always it gets to the Rio de Janeiro. It depends on the intensity of the winds, but the direction is seasonal. The changes in direction of the winds is seasonal.
Thank you.
You're welcome.
Hi, I'm Paula from Brazil. I asked this question. I was doing the in Berkeley Medical Summer School next week, and I asked the same question for another professor, so I'd like to have your opinion. He said that I asked him, can we conclude or can we provide information that the North Atlantic deep water changes is related to human climate change or human influence? And he said that we have the tools, but we don't have enough data yet. And I'd like to know your opinion about that. That's my question. Thank you.
Okay. all stuff related to how the scientific community is proving that the global warming is anthropogenic, mostly. You can get it from the IPCC. The IPCC prepares documents that are very well evaluated and created. I haven't read about, in particular, about the North Atlantic deep water, but I know that it can be done in terms of you can with isotopes, you can measure if the carbon that is inside that is in the ocean has you can trace it. You can somehow know if it comes from mankind or not. It's not my specialty, but I think that someone, or maybe there are already works or articles about that. Someone can, because North Atlantic deep water is being greatly studied. And it's a water mass that has very well-known signatures, characteristics. It's traceable. And so if someone has already measured carbon in this water mass, maybe they have already made a try to answer that question. I don't know, really, I cannot answer that. Thank you very much.
So, a round of applause for Silvia.